ends up being kind of a problematic lab where some of the students done in 10 minutes, and then the next bench over is here's 3 hours struggling and finally gives up and has to come back to makeup week. It's a tough lab. Can be tough. So let's go over at least what the circuit is. You'll be doing the pre-lab and then doing a theoretical report due in 2 weeks. And after we skip this lab, then we end up catching up, so we actually use data in our reports. I believe I've calculated on the FM lab. So let's look at the circuit, because you have to understand what's going on in order to do the pre-lab. So we're going to generate our own AM this time, and signal. Like next week we'll be using an op-amp to do this, but you can use one of these boxes to do it as well. Like the HP3312A, the old one does it. I think another one does it as well. It generates an AM signal. So here's the way the circuit goes. We come into a diode, and then we come into some stages of filtering. C1 and R1 here. C2 and R2. R3 and C3. So this is the envelope detector. What we have is 3 stages of filtering. So this is a first order filter there. There's a first order filter, and then the third first order filter. If you look at these different stages, you can kind of see what they are. First order filters are easy to figure out because you just know that at high frequencies, the caps turn into shorts, right? It just turns into a wire. So this first stage, at high frequencies, it shorts out. That tells us it doesn't pass the highs. It's a low pass filter. Right? Because at high frequencies, it's shorted out. Same here. You can tell that's a low pass filter. Here, the opposite, right? We get a connection through at high frequencies, and at low frequencies it's blocked off. So here we have a high pass filter. Let's go through each stage and understand what's going on. So we've got out of here coming our AM signal. So let's look at that. This is all going to be in the time domain. So here's our AM signal with a preserved envelope we've talked about. Sinusoidal. This is assuming a sinusoidal message. That's our AM signal coming out. Then after the diode, at this point right here, it's easier just to redraw this and erase like I have in the past. The diode prevents any negative current and thus any negative voltage. So we just get rid of the negative portion of the signal. We actually wouldn't see this signal if we were constructing this in the lab. The way we would see this signal is if we got rid of all the filtering and just put a load resistor to ground. Then we would see this, but that's what's happening, even though we don't actually see it in this circuit at any place. All right, next, the low pass filters section. We set it up so that the tau of the circuit is just right to follow the low speed variations of the message, but too slow of a circuit, too much electrical inertia, maybe we could call it, the tau. The bigger the tau, the more electrical inertia. It just wouldn't be fast enough to respond to the quick carrier, high frequency carrier variations. So we want to make that tau just right, so it'll follow the message, but not the high frequency stuff. And you can only do so well with a first order filter, so you're going to get something that looks like this, where, you know, kind of wiggly, but you can see something sinusoidal. We're not following the carrier, but we're not really having a good sinusoid yet. So that's the picture we get out of the stage one here. Stage two, the high pass filter, its only job is, you know, we're trying to get back our message here, which is just a sinusoid. Its only job is to get rid of the DC offset. Remember when we made the AM signal, we put in a DC offset on purpose to preserve the envelope. Now we're backing it out. Now we're getting rid of the DC offset. So that's what this guy's job is to do, just get rid of the spike that's sitting at zero frequency, the high pass. So we'll call this section DC block. So we'll have the same picture, just no DC now, if done properly. So that's that section. And then finally, if all things work out good, have our sinusoid back. This last stage is just what we call ripple reduction. The low pass, but it just cleans up the signal the rest of the way. So that's the way our envelope detector works. So what I recommend doing here, although I don't require it, is you're going to get the most out of this lab, since we're not doing it in the lab, we'll be skipping it, is that you try to model this thing in some flavor of PSpice or your circuit emulator of choice. If you're on a Mac, you can use LT Spice, which is even less user-friendly than PSpice. But when I was fiddling around with LT Spice, I went on YouTube and there's guys explaining it on there, so you can always do it that way. Not a lot of user-friendly, you're not going to find nice user guides with LT Spice. But I think I mentioned that I'm surprised that there's people at JPL that use it, so I mean it's good, it can do heavyweight analysis, but it's not easy to figure out. But it has the advantage that it runs native on the Mac. Of course, now that we're all back on campus, you can always use the Cal Poly computers. They usually have a flavor of PSpice on them. But once again, you don't have to do it, I just recommend it. I decided I'm not going to make everybody do it, because there's some people who just aren't, it's not like MATLAB, where you've been maybe using it all through. There's some people that are real good at PSpice, and there's other people that have never maybe used it, and I don't all of a sudden dump on some thing when you're about to go out the door with your degree and say, now learn PSpice a couple weeks before you graduate. I'm just not going to do that. But if you can pull it off somehow to simulate this, I think you'll get a lot more out of the lab. So let's give you some design equations that are given out for this situation. You might even have gotten them in class. I find that these equations are just kind of get you there in the ballpark. They're not that great, but they get you close, and then you have to fiddle. So if you're simulating this, you can use these equations. So we have one here, RC, which is tau, of course, less than square root of 1 minus the modulation index squared over modulation index times the carrier frequency. I'm sorry, the message frequency. So there's one equation you can use. And then, by the way, this is for determining this first low pass filter getting the tau just right here, at least in the neighborhood with this. Another equation that's given out, 2 pi times the bandwidth of the message. So, for our problem that we have, omega sub m is 2 pi, 5 kilohertz, so 2 pi times 5,000. So that's the same thing right here, omega sub m. The b would be 5,000 in this case. Less than or equal to 1 over RC, less than or equal to the carrier frequency. So these are two design equations that may or may not help you kind of get in the ballpark before you start tweaking values. I kind of like this method better myself if I once again draw out the AM signal. We know, I just kind of thought, you just think about it and you say, I want the transient to die from here to here. Once again, this is just a ballpark, getting you close. You still have to experiment. And if we take like this peak here in the trough, then we know that a transient dies out in like 5 to 7 tau. So if I say, okay, I'm going to make that 7 tau, say, and then I know the period here, so period of the message, across from peak to peak of the envelope, then you can say, there's 2 7 taus in one period, and then you can solve for tau. Tau is equal to the period of the message divided by 14, and tau is RC. So you can set R to be like 1K and then solve for the C, you can do that kind of thing. Same over here. Set one, solve for the other, get a range. Anyways, these can kind of help you out. Once you have this, you're going to have two, when you hook up, say, the recommended way to do this is to do it a stage at a time. So first just do this stage and don't have the next two stages and just try to get that picture. And then once you got that, keep adding subsequent stages. Like say if you're working on here on your P-Spice and you hook it up and you get something that looks like this. This is telling you your tau is too small, right? It's too fast to circuit. It's not sluggish enough. It's following the carrier. So what do? Turn up larger value for R or for C. Turn it up a little bit. And you should start getting something like this. What if you get like a straight line across here? Then you've got too big a tau. They can't even follow the message, let alone the carrier. Turn down R or C until you start seeing, hey, I got the sinusoidal shape. Yeah, there's some ripples in there, but I can see in there the sinusoid, just like you can see the sinusoid here. We'll be able to do it up here too. Yes?
Do you use the same values for RC for each stage?
No. You want the same taus for here though. Yeah. These will be the same taus, but I'm kind of getting to talking about this stage in a minute. So once you got this and you got that picture, then you just want, this is kind of a simple stage because you just want to eliminate that spike that's sitting there at 0 frequency. So the only thing you got to worry about is you've worked real hard to get that nice picture. If you have a capacitor that's too close in value here to C1, you can mess up your picture. They kind of interact and then you mess things up. So it's like a pole zero plot, and you've got two poles right on top of each other. They interact with. So make C2 just like an order of magnitude bigger or smaller than C1, and then that should be okay. And then, as we just said, if you think about it, the tau on this better be the same as the tau on this because you're trying to follow the message. It's just that you have to take into consideration that maybe your R and C You know, you can play with either R or C to get the same value. If you have a big R on this stage, you're gonna drop, you know, this is a voltage divider, you're gonna drop all your voltage across this R and have a little left over to come out the output. So you've gotta think about that. You know, you're gonna have to play with this voltage divider to make sure you don't just get kill all your signal here and steal it and have nothing for the output. So those are kind of just some rules of thumb and some things that you can think about as if you're designing this. You're actually going to have to come out with whether you model it or not, the pre-lab asks you to use these and come out with a C1 and an R1. But I'm hoping that you guys will put in a little effort and try to model this and make it work. This is one of those, this is for sure my voodoo lab. If you've ever worked with like RF engineers, I don't know if you've ever hung around them or worked with them or know about it. This is kind of reminds me of that. They're kind of like the voodoo witch doctors of ECE, because they design a circuit and then they hook it up and see if it works. Oh, it doesn't work. They pull out the roll of foil tape and start putting tape all over the circuit. Does it work now? Does it work now? You know, it's just, RF is just kind of voodoo a lot of times. You don't know what's going to happen. And this lab does that. People with the exact same values of R's and C's, two different benches, one group is gone, it worked in 5 minutes, the other groups can't get it to work in 3 hours. It's just one of these weird labs. So you'll be glad to skip this one, but you still have to at least do the theory and maybe model it. I think that's all I got on this. Any questions? All right, I'm going to erase that in a second. We'll talk about tonight, so if you want to take a picture of that, now's the time.